In this video, I'm going to explain diffraction at a single slit. Let me start with the experimental arrangement as the first part. Here we have a monochromatic source of light of wavelength lambda. Okay, which is placed at the principal focus of the lens L1, which converges all the rays parallel to each other after refraction. So we have a plane wavefront which gets incident on a narrow slit AB. So we can have the width of the slit is small a. A screen is placed at the focal plane of a convex lens L2, which is at a distance capital D from the slit, on which the diffraction pattern is obtained. We are going to obtain diffraction pattern on the screen. Now let us go to the formation of diffraction pattern. According to rectilinear propagation of light, a bright image is expected at the center of the screen. But in practice, we get a diffraction pattern instead, which means that we get a central maximum at the center O, followed by a number of dark and bright fringes called secondary maxima and minima on either side of the point O. Now we can go to the formation of central maximum. According to Huygens principle, when light falls on the slit, it becomes a source of secondary wavelets. These are the wavelets. These red dots are the wavelets. These wavelets are initially in the same phase and spread out in all directions. Let C be the center of the slit. Now let us consider the wavelets which fall on the lens in a direction parallel to CO. They get converged to a point O, meeting in the same phase. They will all meet at O in the same phase. The waves from these wavelets superpose each other and give rise to the central maximum around this point O. This is the central maximum. Now let us discuss the position of the secondary minima. Consider a point, an arbitrary point P on the screen, at which the wavelets sending out waves in a direction making an angle theta with CO direction. They converge to a point P lying on the focal plane, which is the screen. The waves from the wavelets from different parts of the slit do not reach the point P in the same phase, although they are initially in the same phase. It is because they do not cover equal distance from the slit to point P. Let us consider these two rays, the path of these two rays from A to P and from B to P. They have path difference. Okay, their path difference will be equal to Bn. So we can say this length and the length of A to P and N to P is same, or Bn is the path difference between A to P and B to P. Let's have a closer look at a right angle triangle ABN. Here this is theta. If this is theta, this is 90 degrees, so this will be 90 minus theta, and this will be theta. This will also be theta. And the width of the slit AB, this is A, B, N. The width of the slit AB is A. So sine theta will be what? Sine theta will be perpendicular by hypotenuse. It is BN by hypotenuse is A. Then we can write BN equals to A sine theta. Remember that BN is the path difference between these two waves. The waves from A to P and B to P. Okay. This is the path difference. Now let us choose a point P such that Bn is lambda. Bn is equal to lambda. That is the path difference between these two rays. The rays from A to P and B to P. Okay. For such condition, theta, this theta be theta 1. The angle is theta 1. This will be theta 1. Let us divide the slit into two equal parts, AC and CD, such that CD will be lambda by 2 because Bn is lambda. It is from similarities. Here CD is parallel to Bn, CD and Bn are parallel. So AC is half AB, AC is half AB, which gives CD is also half Bn. So we can write CD is lambda by 2. If the path difference between the two waves is lambda by 2, path difference lambda by 2 means this is one wave, this will be another wave. It means they are in opposite phase, they are in out phase. They cancel each other. Okay. So we will have a minimum intensity on P. Let us have a closer look. Here, let me name the wavelets on the two parts of the slit. 1, 2, 3, 4, 5, 6 from the first part of the slit and 7 to 12 from the second part of the slit. This is the first part, second part. Okay. 1 from first part and 7 from the second part. They will have path difference lambda by 2. 2 and 8 also having path difference lambda by 2. 3 and 9 also. 4 and 10. 5 and 11. 6 and 12. That means the pair of each pair has path difference lambda by 2. So we can say that they superimpose destructively at point P. They cancel each other. So we will get a dark pattern on the screen at point P. The present position of P, the position of P now is the position of the first secondary minimum, or the first secondary minimum. So we can write for the first secondary minimum, it will follow sine theta 1 will be equal to lambda by A. Okay, this is for the first secondary minima. Now let us choose another position of P such that Bn is equal to 2 lambda. Bn is 2 lambda. In this case, let us divide the slit into 4 equal parts. They are 4 equal parts. For this position of P, let theta be theta 2. If this is 2 lambda, it will be CD will be lambda, and this length will be lambda by 2. It means the path difference between this pair 1 and 4, 2 and 5, 3 and 6 will be lambda by 2. That means they will interfere destructively. Likewise, these pairs 7 and 10, 8 and 11, 9 and 12, they interfere destructively. So all the wavelets superimposed at P producing the destructive interference. Such a point is called the second secondary minimum. For the second secondary minimum, we can write sine theta 2 is equal to 2 lambda by A. Okay. The position of P for this condition is called the position of the second secondary minimum. In general, let us write Bn equals to n lambda, because we get secondary minima when Bn is equals to lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda till n lambda. Okay. For general, we can write Bn equals to n lambda. For this condition, theta will be theta n. So sine theta n will be what? Sine theta n will be n lambda by Bn by A. Sine theta n is n lambda by A. And if you look at this triangle POC, in triangle POC, Yn is, let us write tan theta n. Tan theta for this condition, theta will be theta n. Tan theta n will be Yn by d. Yn by d. For small angles, sine theta n is nearly equal to theta n, and also tan theta n is also nearly equal to theta n. We can replace sine theta n by theta n and tan theta n by theta n. So we can equate these two equations. So we can write Yn by d equals to n lambda by A, or Yn is equal to n lambda d by A. This Yn gives the position of the secondary minima, the nth secondary minima from the center of the screen. Or now let us calculate the width of the secondary maxima from the position of the secondary minima. Here we have the secondary maxima. If we subtract the position of the nth minima, if we subtract the position of n minus 1th minimum from the nth minimum, we will get the width of this maximum, the secondary maximum. Okay. So width of the secondary maximum will be equal to beta equals to Yn minus 1, Yn minus 1. Then what do we have? Yn is n lambda d by A minus n minus 1 lambda d by A. We will get n lambda, we will get lambda d by A. Since the width of the secondary maxima is independent of n, they are of equal width. Okay, the secondary maxima are of equal width, same width, equals to lambda d by A. Now let us try to find the positions of the secondary maxima. To get maxima on the screen, we have to divide the slit into 3 equal parts, part 1, part 2 and part 3, such that dn is equals to 3 lambda by 2 for the first secondary maximum. If this is 3 lambda by 2, this will be 2 lambda by 2, that is lambda. This will be lambda by 2. Okay, it means the wavelets, consider the wavelets at these two positions, at A and this position. They will produce a waves of path difference lambda by 2. So the pairs 1, 5, 2, 6, 3, 7 and 4, 8 and 8 will produce waves having path difference lambda by 2 each. That means they cancel each other, or we can say they superimpose destructively in pairs 1, 5, 2, 6, 3, 7, 4, 8 of part 1 and part 2, and part 3, this will produce dark fringe. They destructively interfere. And part 3, if we look at part 3, the wavelets in part 3 are unused. So this will produce the bright band on the screen, which means that 1/3, it will have the intensity 1/3. These wavelets on part 3, wavelets of part 3 will produce a maxima, which will be having intensity 1/3 of the central bright band. Okay. And for this condition, we can write Bn equals to 3 lambda by 2. That is the condition for the first secondary maximum. Here theta will be theta 1 dash. Then we can write sine theta 1 dash will be Bn by A. It is 3 lambda by 2A. If Dn is also equal to 5 lambda by 2, we will get the secondary maximum. So we can write sine theta 2 dash equals to 5 lambda by 2a if Dn is 5 lambda by 2a, and sine theta 3 will be 7 by 2 lambda 7 lambda by 2a, and so on. The nth secondary maximum will be produced when sine theta n equals to odd multiple, so it will be 2n plus 1 by 2n plus 1 lambda by 2a. Again, if you look at this triangle POC, we can write tan theta n dash, and this will be theta n dash. It will be equal to perpendicular by base yn dash divided by d. Since theta n is very small, sine theta is equal to sine theta n, and tan theta also replaced with theta n. So we can equate these two equations. If we equate these two equations, we get yn dash by d equals to what? 2n plus 1 lambda by 2a. Then yn dash will be 2n plus 1 lambda d by 2a. Okay. So yn dash is the position of the nth secondary maximum from the center of the screen, or the secondary minima lie between the consecutive secondary maximum. These are the positions of the secondary maximum. They are the consecutive secondary maximum. This is the n minus 1th secondary maximum, position of the nth secondary maximum. So the width of the secondary minima will be yn dash minus yn minus 1 dash. Yn dash is 2n plus 1 by 2a lambda d, and yn minus 1 dash will be 2n minus 1 plus 1 lambda d by 2a. Then what do we get? 2n lambda d by 2a plus lambda d by 2a minus 2n minus 2 plus 1 by 2a lambda d. Minus 2 plus 1 is minus 1. So n lambda d by a plus lambda d by 2a minus 2n lambda d by 2a minus minus into minus plus lambda d by 2a, 2 and 2 cancel. So n lambda d by a and lambda d by a, they cancel each other. Lambda d by 2a, lambda d by 2a. If we add these two, we get 2 lambda d by 2a. It is lambda d by a. It is again independent of n. This is the width of the secondary minima. They are of equal width. This is how the pattern, the maximum and the maxima and minima are distributed on the screen. This is the center of the screen, and this is called the central maximum. This is the first secondary maximum, second secondary maximum, third secondary maximum. Okay, even on this side. The secondary maximum and the secondary maxima are having equal width, but they have different amplitude, different intensities. It is decreasing in intensity on this side, even on this side, decreasing intensity on this side. These are the positions of the dark band. These are the dark band. These are also the dark band on the other side. This is the position of the first dark band. This is also the position of the first dark band on the other side. We calculated in the previous part that y1 is equal to d lambda by 2a. The width of the central maximum will be equal to y1 plus y1, that is 2y1. Beta naught denotes the width of the central maximum, so it is 2y1. y1 is equal to lambda d by 2a, then we get beta naught equals to lambda d by a. This is the this is the width of the central maximum. Thank you.